Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit 12, Lesson Number 4, the Paraboloids. On a personal note, this is the last new lesson in Math 4 Honors, and it'll be the last lesson that we put a video up for. There were some at the beginning of the course that we didn't finish this academic year, but we'll get to those next year. But this is it for now. I hope that you've enjoyed the videos and they've been helpful. What we're going to do in this last lesson is we're going to use a variety of techniques to look at one type of multivariable function, one type of surface in multiple variables, a type of surface called the paraboloid. It's okay to think about this kind of as the three-dimensional version of a parabola, but that may be a little bit misleading as well, as we'll see in one of the cases. So let's jump right into it. Exercise 1 asks us to consider the function f of x equals x squared plus y squared minus 9. The first thing we're supposed to do is find the intercepts of this function. Why don't you pause the video now, use your algebra, find the intercepts, and then we'll move on to letter B. Alright, well, the intercepts are pretty easy, and they all exist, which is kind of nice. What do we have? Well, for our x-intercepts, we would set y and z equal to 0, and we'd have x squared minus 9 equals 0, and x would be plus or minus 3. For the y-intercepts, we'd set x and z equal to 0, and we'd get y squared minus 9 equals 0, and y equals plus or minus 3. And to get the z-intercept, we will literally evaluate f of 0 comma 0, and that's negative 9. So that's my z-intercept. With a multivariable function, there can be only one z-intercept, but multiple x and y. Let's take a look at B. What are the domain and the range of this function? Why don't you pause the video now and think about what you would write down about these two. All right, let's do it. The domain, right? Remember here, domain is an issue of both x and y. But there is absolutely no restriction. I can put any x or y value in. So the easiest thing to say is not all. I say all real values, but that's not a good thing to say. I'm going to say the entire xy plane. In other words, if I do a real brief sketch of my x, y, and z, I can pick any point from my xy plane and it's going to give me a z value. Now the range, that's a little bit more difficult, but it's not too bad. Keep in mind that x squared plus y squared must be greater than or equal to 0, right? Therefore, x squared plus y squared minus 9 must be greater than or equal to negative 9. And there's my range, right? Z is greater than or equal to negative 9. All right. Letter C, describe the level curves of this function for values of z within the range specified in part B. Give some examples for various values of z. So let's get a feeling for this. The smallest z can be is negative 9, right? So this is actually kind of interesting. Let's experiment with this. Let's let z equal negative 9. Something a little weird happens here, right? When we look at the level curve, we actually have x squared plus y squared equals 0. You know, I'm all ready for a circle, and what in the world is this? This is actually just a point, right? There's only one point. The point 0, 0 has a y value of negative 9. Sorry, a z value of negative 9. I apologize. Let's do something like z equals negative 8, right? In this case, we would have x squared plus y squared minus 9 is equal to negative 8. And that would give me that circle, x squared plus y squared equals 1, right? So we have a sense for this, right? We could keep doing it. You know, anything bigger than 9, let's go generic now. Let's say z is equal to k. We're going to have x squared plus y squared minus 9 equals k. So x squared plus y squared is going to be k plus 9. And of course, all of these things are circles, right, that have a center at 0, 0. And have a radius equal to the square root of k plus 9. This might be a little bit abstract, but the good thing about it is it tells me that as the z value which I know we called k. As the z value gets larger, the radius of the circle gets larger. But all of these level curves are circular. Now, all of this is driving towards us trying to get a feeling for what's going on with this function. So right now what I know is if I slice it horizontally, my level curves are circles. I know these looked elliptical, but except for the one right at the bottom, which is like that. So I'm not really sure why it's called a paraboloid yet, right? That's going to come in part C, part D, and part E of the problem. So I'm going to clear this out, copy down anything you need to. All right, it's gone. Bada bing, bada boom. Here goes exercise 1, letter D. This is the first time we're going to talk about these things, what are known as traces. Traces are really super cool, and we've already been doing them. When we have been thinking about contour lines and level curves, we've been slicing a surface with a horizontal plane to really kind of get a sense for what the intersection curve looks like. In this case, they're actually all circles. But we can also slice with vertical planes, either parallel to the XZ plane or parallel to the YZ plane. All right? I want you to all try to picture what y equals 3 looks like and what x equals 2 looks like, right? Real quick sketch of y equals 3. A terrible sketch, but we'll do it anyway. Remember, we looked at these in the last lesson. 1, 2, 3. So it's like vertical knife, kind of like that. It's going to slice. I got to get rid of all this text. All right, so let's describe the vertical traces. All right. The way that I'm going to do this is I'm just going to take 3 and I'm going to substitute it in for y. And now what's interesting is we're kind of left with this. I'm going to use z instead of f of xy. I get x squared plus 3 squared minus 9, and z is equal to x squared. Well, that's a parabola, right? A parabola opening upwards. All right, we'll get a visual on that one in a second, okay? Same thing with x equals 2. I can substitute that in and I'll get z equals 2 squared plus y squared minus 9. So z equals y squared. That would be 4 minus 9 minus 5. That's also a parabola opening upward. All right, so this is kind of cool, right? Opening upwards. What I know is that when I cut this surface horizontally, I'm getting circles. And when I cut it vertically, I'm getting parabolas. It's because of that vertical slice ending up being a parabola, vertical slices, because those vertical slices are parabolas, that's why I call this a paraboloid. It's not why I call it a paraboloid, it's why everyone calls it a paraboloid. All right? Now, asks us to sketch this. Sketching these things is always interesting, always a challenge, and kind of questionable in terms of a skill set. But I'm going to give it a shot anyway. You very well may have to do this in your college calc class at some point. Now what I'm going to do is I know that the thing bottoms out at -9, okay, down here on the z-axis. And what I know is that it's always giving me parabolas in the cross sections, right? So watch as I draw on a parabola that's sort of in the YZ plane, okay? That would literally be if I let x equal 0, all right? I can also draw a parabola, and this is much harder, in the XZ plane. Now, this is going to look terrible, but I do know what all these intercepts are. Whoops, that wasn't the 3. This was supposed to be the 3. This is supposed to be -3. And what I also know is that all of these cross sections are circular. Those are those level curves Wait until you see my next picture. You think this is bad? Wait until I draw a hyperbolic paraboloid. Right? It could have been worse. Not much, but it could have been. As I said, wait until the next exercise. I slice it horizontally, I'm getting circles. I slice it vertically, I'm getting parabolas. How do I know that? Because that's what I always find when I substitute one equation into another. I find out what their intersection looks like. When I substitute one equation into another in two-dimensional space, all I get are a point or a series of points, right? On the other hand, when I have no room left. On the other hand, when I take a surface, something with area, and I substitute in another surface, like a vertical or a horizontal plane, the intersection no longer becomes an isolated set of points, but becomes a curve itself. That doesn't look horrible. Let me clear this out. All right, gone. So circular paraboloids, the one that we just looked at was z equals x squared plus y squared minus 9. This one, the kind of generic one pictured here, is very likely z just equals x squared plus y squared. That's the most basic one. What I'm going to do now is I'm going to actually open up my grapher. Okay? So let me open up grapher now. And what I'm going to do is I'm going to open up a graph of the paraboloid that we were just looking at, x squared plus y squared minus 9. The reason it's called a circular paraboloid in this case is that all of the level curves where we set z equal to a constant, slicing it horizontally, all of them are circles, right? So let's take a look at this thing. We've got the grapher open. It's a little bit hard to tell again because the thing actually extends up to infinity. That's that whole range is greater than or equal to -9. Right? What's cool is we can actually look at those vertical traces. In other words, let me also turn on y equals 3. Let me click that right now. And what you see now, especially if I rotate it, is you see that the intersection of that vertical plane, y equals 3, with the paraboloid gives us a parabolic curve sitting there. Let me unclick that one. Let me actually click on x equals 2. Okay. And when we do that, of course, what we see now is a vertical plane at x equals 2. And we also see a parabolic intersection. Again, when we slice it vertically, if we get parabolas, it's a paraboloid. Okay. One last thing. Why don't we take that off? And let's click on, I think it's z equals 4. Click on that. And now we've got that thing that's going to give us our level curve, right? Let me actually rotate the paraboloid. All right. Granted, it's a weird view, but you can definitely tell by just staring straight down inside of it that what we've got there is a circle. All right. Let me rotate the parabola back up. And let's close out grapher. All right. Grapher is closed. Let's go on. Let's analyze something else. So the key to analyzing three-dimensional functions, or functions with two input variables, I think boils down to understanding the intercepts, understanding vertical traces, i.e. intersections when x is a constant or y is a constant, and I think understanding level curves. So in the next one, we're going to look at what's known as a hyperbolic paraboloid. A hyperbolic paraboloid. And even the name gives you a clue for what's going on. We know that when we cut it vertically, we're going to have parabolas, and when we cut it horizontally, we're going to get hyperbolas. But let's play around with it. In fact, what I'd like you to do is pause the video now and just figure out as much as you can about this surface. Intercepts, traces, all that kind of stuff, all right? Pause the video now. All right, let's go through it. Let me play around with intercepts, right? That's a good place to start. Intercepts. Let's go x-intercept. Okay, to get x-intercepts, we'll set z equal to 0, y equal to 0. I know you've done this quite a bit. I get 0 equals 0 minus x squared plus 1. I get x squared equals 1, and x equals plus or minus 1. Great. Let me do my y-intercepts. All right, let's set z equal to 0. Let's set x equal to 0. I get y squared equals -1. Oh, whatever. So I get no y-intercepts. Trust your math. And the z-intercept, all right, that's just going to be g of 0, 0, which is going to be 1. All right. So no y-intercepts. That's interesting. Somehow this hyperbolic paraboloid, I don't know if I want to say runs parallel to the y axis, but never touches it. All right, what should we do next? Why don't we hit the level curves, right? Constant z values. All right, well, we could pick a z value to play around with. Let's pick a z value of 2. Say I had z equals 2. I'd get 2 equals y squared minus x squared plus 1. Maybe get that all over there. All right, what is this thing? It's a hyperbola. Why? Because both x and y are being squared, there's a subtraction, etc. It opens up around the vertical. In fact, if I absolutely had to, I could probably sketch it. It would take me a little bit of time, but it would look something like that, right? I'm going to do another one. I'm going to use z equals 0 for a second, because something strange happens. In fact, I get -1 equals y squared minus x squared. Now that's a little bit deceptive and poorly written. I'm going to actually get 1 equals x squared minus y squared. This is a very, very similar hyperbola to this one, except it sort of switches its orientation, right? It now opens up around the x-axis. Beautifully done, Weiler. It looks something like that. So this is interesting because as I slice it vertically, sometimes I'm going to get level curves that look like the one up here, and sometimes I'm going to get them that look like this, all depending on where I slice it. Okay, let's go with vertical traces. All right, I'm going to run out of room, so my head's going to end up having to cover up something important, probably something over here, to be honest. Vertical traces. So let's kind of visualize what would happen if I put x equals 2 in, right? Now remember, the idea there, because this is hard to picture, right, is that I would be taking the plane x equals 2, and I'd be slicing this curve and thinking about what I got. So what would I get? I'd get z equals y squared minus 4 plus 1, so z would equal to y squared minus 3. Well, we know what that looks like, right? That if I was graphing in z and y, that would kind of look something like this. Right? It's definitely a parabola that opens upwards. Right? So in other words, if I were to sort of be starting to fill this in, I might get some kind of intersection that looks like that. Let's go with another trace. So let's do a y equals. Let's say y equals, why not? Why not go with it? Let's say y equals 2. Okay, now again, the idea here is that I go out 2 units on the y-axis. I have that plane. Oh man, is that a beautiful picture? The question is, how does that cut the surface? Well, let's take a look. We get z equals y squared, which is 4 minus x squared plus 1. Z is equal to 5 minus x squared. That's also a parabola, but notice it actually opens downward. Hey, it's the bell. So I get something like that. Oh, boy. Wow, I don't even have enough room to do the sketch. Oh my goodness. Well, okay, so what do we have? I'm not even sure if I should do the sketch here. Let me, I wish I could just circle and erase all at once. I apparently don't have the ability to do that. Let me just get rid of this and show you how bad I am at drawing hyperbolic paraboloids. I was bad at it when I was in Calc 3. I continue to be bad at it, and boy, I tell you, the tablet does not help. All right, but let's give it a shot. Okay, so what do I know? You're going to love this. I do what a lot of drafts people call a wireframe model. All right, so let's take a look. X, Y, pardon the noise out in the hallway. Let's see, what did I have as my x-intercepts? I had 1 and -1. Yay! My y-intercepts, I didn't have any. My z-intercept was 1. Yeesh. Let me think just about my vertical trace at x equals 0. If I had x equals 0, what would I have? I'd have z equals y squared plus 1. Well, that just is a parabola. Whoops. That's a parabola that looks something like this. Right? Remember, you're just kind of caught in this plane. Draw this down. And let me actually look at, let me go back and look at, oops. Go back and look at the trace when y is equal to 0. Right? That's going to be the xz plane. Well, if y is equal to 0, z is equal to 1 minus x squared. That would be a parabola that kind of looks like this. All right. Oh my goodness. So we're going to always get these sort of concave down parabolas in this direction. And we're always going to get these concave up parabolas in this direction. Isn't that beautiful? And somehow, when we cut it horizontally, we're going to get hyperbolas. I think that picture says it all. I was going to go to Grapher, but that's a great picture. Or not. Let's clean this thing up. Let's take a look at it on Grapher. All right. No, Math 4 Honor students, you won't have to draw a hyperbolic paraboloid, but I'd like you to be able to analyze it, okay? Clearly, I can't draw it myself. So let's open up Grapher right now. Actually, do I have this on another page? Ah, yes, there we go. Let's open up Grapher now. All right, so we got plenty of room. All right, I'm going to open up the hyperbolic paraboloid, and this is that hyperbolic paraboloid. This is the thing that looks like a Pringles potato chip. In fact, if you go into like Google Images and you search hyperbolic paraboloid, a bunch of the hits that you'll get will be on Pringles potato chips. It's hilarious, but very true. A lot of times you will also see hyperbolic paraboloids when you look at tents. A tent is oftentimes a hyperbolic paraboloid. So it's kind of cool because we've got this thing up, right? We can rotate it. Take a look at this one particular point. There's this one point on a hyperbolic paraboloid, a very, very important point called a saddle point. All right, a saddle point is exactly what it sounds like. It's like the point of a saddle. It's like that place where you've got a concave down parabola meeting a concave up parabola. You know, so you could have your legs going across the saddle this way, and then the saddle is sort of pointing this way, as if that helps. But anyway, let's take a look at what we just looked at. Let's first slice this with a constant x value, okay? And look what happens. When we slice it with a constant x value, we're getting concave up parabolas. Let me take that off. Let me now slice it with a constant y value. And look at that. We now have a concave down parabola. Rotate a little bit. Isn't that cool? Let me get rid of that. Now let's take a look at some of those level curves. Now remember, the level curves were all hyperbolas. That's why it's a hyperbolic paraboloid. But what was weird was they had different orientations, you know, in terms of opening in the y direction versus opening in the x direction. So let me do one where we've got a positive z value, okay, and click on that. Now what I'm going to do is I'm going to rotate this thing so that you can see it sort of from the top view. Do you see the hyperbola there? Do you see the way that it's opening? Keep that in mind. Let me just rotate it back. I'm going to click off on that. Now let's click on the other vertical plane. I'm sorry, click on the other horizontal plane, the other constant z value. Now that one's kind of lower. It's got a value so that now that if I rotate it, you'll see that the hyperbola points in the opposite direction. Let me rotate that back. I'm going to click off of that. And the last thing I'm going to do, I'm going to click back on the normal surface, and I'm going to turn on those contour lines. So let me go in, turn on the contour line, back out, take a look. Those contour lines are like I slice the thing repeatedly with a horizontal, and I can see those hyperbolas. All right. So the cool thing about a paraboloid in general is that the name paraboloid comes from the cross sections with vertical traces. So when the vertical traces a parabola, it's a paraboloid. This is really all about the level curves. Right? It's just a naming system. That's all it is. I used to have the hardest time remembering whether or not a Pringles potato chip was a hyperbolic paraboloid or a parabolic hyperboloid, right? And there are hyperboloids. But for a hyperboloid, the vertical trace has to be a hyperbola. All right. So I'm going to clear out the text, and we're going to go on to one last exercise. All right, consider the surface defined by z equals 16 minus 4x squared minus y squared. Analyze this function using intercepts, level curves, and vertical traces. Then draw a sketch of the surface. Explain why the surface is known as an elliptical paraboloid. All right, so pause the video now and go through your analysis, see what you get, and then we'll go through it. All right, well, elliptical paraboloids aren't too bad to sketch. Why not? Let's get our intercepts. We're going to do this quickly since we're sort of running out of time. I'm just kidding. Anyway, what do the x-intercepts look like? 0, 16, 4x squared, 0. So I get negative 4x squared equals negative 16. X squared is 4, and x equals plus or minus 2. So there are my x-intercepts. My y-intercepts, 0, 16, 0, y squared. Eventually we'll get y plus or minus 4. Let's not waste our time. And the z-intercept will be 16. All right, so not too bad. Traces. You know, I'll tell you, after the last exercise, it made me realize something. With traces, it's actually very easy, well, maybe not easy, but it's very oftentimes helpful to do some basic traces. All right, for instance, one trace that's good to do is x equals 0. That is literally what's known as the YZ plane. All right? And if I put x equals 0 in there, what I end up getting is z equals 16 minus y squared. So a parabola that opens downwards. Right? So that's something like this. Right? In z and y. Yeah, that's going to start getting confusing. All right? If I do y equals 0, x, y, z. If I do y equals 0, we're talking about the xz plane. All right, and of course y equals 0 will give me z equals 16 minus 4x squared. Also a concave down parabola, but one that's more narrow, right? It's been stretched out, like silly buddy. Now, last thing, but certainly not least, would be your level curves. Now, again, we could choose many different z values, but one that is oftentimes very helpful is z equals 0, because again, that's the xy plane. And if we do that, if we put z equals 0 in, we get 16 minus 4x squared minus y squared equals 0. And that would be 16 equals 4x squared plus y squared. And that is, of course, as we all know, an ellipse. And to me, this is actually enough. I can do a little bit of a sketch now. It's not going to be a great sketch, and then we'll do grapher to look at something a little bit better. Right? Z, x, and y. So let's do our x-intercepts. There, 1, 2. 1, 2. Our y-intercepts are 1, 2, 3, 4. 1, 2, 3, 4. Our z-intercept's way up here at 16. I'm not going to try to scale it right. Then if we look at x equals 0, what happens is we get this parabola. If we look at y equals 0, we get this parabola. Ooh. And then our level curve, at least in the xy plane, is this ellipse. And what would happen is every z value that's within the range, z less than or equal to 16, would give us an ellipse. Now, these probably look just as much like circular as anything else, but there it is. Of course, it's known as an elliptical paraboloid because its vertical traces are parabolas, but its horizontal traces, also known as level curves, right, are ellipses. Let's take a look at one last one. Let's bring up Grapher. All right, it's on our screen. Right there is our elliptical paraboloid. Again, it's a little bit hard to see, and I apologize for that. Maybe by next year I'll have a better piece of software on here. But here we have it, right? And again, we can cut it with that x equals a constant. Let me do that. And look, we have a concave down parabola. Let me unclick that. Let me now click on a y equals plane. Notice we have a concave down parabola again, but thinner, right? That was that stretched out parabola. And let me click on a level surface, or let me click on a constant z value. All right, let me rotate that thing. And now when you're looking right down on top of it, it's pretty clear that the cross section there is elliptical. All right, let me rotate it back up, and I'll get rid of Grapher. All right, let's finish up. Well, that was a lesson. Unit 12, lesson number 4, and it's officially the last lesson of Math for Honors. I hope you've enjoyed the video. I hope you enjoyed the small unit on multivariable functions and their graphs and their domains and their ranges. Important stuff, especially once you get into third semester calculus, which no matter where you go to college, man, does that course move quickly. So it's good to have this background information. Thank you for joining me, though, for one last Arlington High School Math for Honors lesson. My name is Kirk Weiler, and until next time, which may be next year, keep thinking and keep solving.